Okay, hello. Welcome to a intro on exponential functions. There are going to be a handful of videos here that are going to try to introduce you to the whole concept of stuff that's exponential in form, maybe in a different way than you've seen in prior videos or before in the past. So if it's a little different, no big deal, and just try to hold on tight. If you need something, review the video or rewind it. I'm going to ask you a couple things which are really important normally, but and I say them quite often, so I'm going to ask you big time this time. Please participate, and as we go forward here, pause the video and do the little exercises. And as I'm talking here, make sure you get out a couple pieces of paper too. You'll need those going forward. Just blank pieces of paper that you don't care about, because as we do this, we're going to make a little bit of a mess if you play along as if we were in a real face-to-face class here. So before we get going, let's just warm up a little bit. And um, the warm up problems didn't really come out all that well on the document here, so we'll only do a couple of them. But remember, just from the past with our exponents that we've already done, that if you're looking for part A here, and I ask you what 3 squared is, that's just really 3 times 3. In other words, yeah, you should be almost laugh and say, well, that's 9, that's a piece of cake. But remember that when you have a base that's 3 and an exponent that's 2, all that exponent does is tell you how many times that base multiplies by itself. Likewise, for part B, 2 to the third power says that we need to multiply that base 2 times itself 3 times. So 2 times 2 times 2, oh, I think that's 8. And even if there's a number out in front here, the whole order of operations thing, since I'm running out of room already, really means that you have to do, if you're following PEMDAS, remember, please excuse my dear Aunt Sally. So exponents have to come first. I'm sorry, parentheses and then exponents. So there's no parentheses, but then exponents come next. So in this case, for part C, it would be 2 times 5 times 5, where we have to do that part first, which is 25 or 50. So real quick here, try to do part D. Pause the video and give that a quick shot. Okay, if you're back, you should be telling me, hey, that's just 3 times 1, 2, 3, 2, 4 times. And if you have that, remember you got to do all this part first. We got to do our exponents first. 3 times, well, 2 times 2 times 2 is 8. We knew that from the previous example. Times 2 would be, what, 16? And then 3 times 16, I think, is what, 48? So that should be good enough for a warm up. And you can do a few more problems down here. I only do a couple more. But there's different ways to write multiples by things. In other words, if you had, and I'm looking at that one right there, 3 times itself 5 times, you could write it this way in the other version, right? If you wanted to simplify it. But be careful, that's not the same as adding 3 5 times. So that's just really taking 3 and multiplying it by its, 5 times, which would be in this case here. So we could take the time and go match these things up, but really this top one's going to be 15, while that bottom, if you do it on a calculator, I think it's 243. Okay, so make sure you do your parentheses and exponents first. And now for the fun part, let's go down here. And if we were in class, we'd be doing this as a group, but because I'm pretending that you're sitting there next to me, I mentioned earlier that you need a piece of paper. So go ahead, pause the video, get a piece of paper. And so pause the video now, come back when you have one. Okay, now I'm assuming you're back. Now, if you're back, what I'd like you to do, and we can read this, it's called a paper tear problem. And I want you to start with a single piece of notebook paper. And what I want you to do is before you do any tears at all, and we're going to make a table here simultaneously. So before we tear it, we have one piece of paper. Does everybody agree? And what I want you to do now, and I'm being serious, play along, take that piece of paper and tear it in half and stack the two pieces on top of one another. And it might seem like a silly exercise, but I want you to tell me after one tear, this is going to stand for tears. I want you to tell me how many pieces you have, or pieces of paper. So after one tear, if I'm not mistaken, you have two pieces of paper. And thank you for playing along. I don't know where that went. Let me see if I can get that back here real quick. I apologize. I used to worry about things like that, but now these videos, you just kind of roll with the technology. So now after one tear of a piece of paper here, you're going to have, what do we say, two pieces of paper. Okay, now out of that stack, you should have the two pieces, one on top of the other. The tears don't have to be perfect. You don't have to even use scissors. It's just kind of just do it real, crudely. Crude tears, doesn't matter. I want you to tear it again. And after two tears, and you stack all your pieces of paper, go ahead and count them. How many pieces of paper do you have? And again, I'm pretending you're playing along. And I believe you should have four pieces of paper. Now, as you do this over and over again, let's go ahead. Let's do a third tear. Remember, of that stack of your four pieces of paper, and you tear everything right down the middle again, right in half, and stack them. How many pieces do you have? And if you're telling me 8, you would be correct as well. So humor me, do it one more time. Stack your pieces of paper. And by now you might not be counting. But just if you've noticed, every time this number here is now double the output from before. So if this is the input and the output is here for y, you should be noticing a pattern. And even if I ask you to tear it again into 5 pieces, you should be able to tell me that that should come out to be 32. Now, if you were in a group, I'd say, hey, look for a pattern, and I kind of gave it away. But when you increase the output by 1, the output doubles. So at first thought, you might think that we could write a linear function. And remember, linear functions are like this, where the slope has to be the constant average rate of change. And I'm going to erase this in a second. But if the slope is a constant average rate of change, remember in the past, we've been able to check that. And you could take 2 points like these two. You could say 4 minus 2 over 2 minus 1, for instance. And that would be 2 over 1, and that's 2. Well, then let's check these points. Remember, to have a linear function, it has to work the same average rate of change to be a straight line for every value. And I hope you're okay with this reviews because some of you might not remember. But 8 minus 4 over 3 minus 2 is then 4 over 1, which is 4. So 2 is different than 4. And if this differs, our number, what happened? If our number differs just once, then we don't have a linear function that can model it perfectly. So that's how we're going to test for linear functions later on. So just remember that. And if I went ahead and erased that information, so you know it's not linear, and the answer to that is because there's not a constant average rate of change, or it's not the same slope everywhere. So that's what you need to write for part C. Is the function from part A linear? No. There isn't a constant average rate of change. So that just means there's not the same slope everywhere. You can hear my kids in the background. Okay, so if it's not linear, I'll tell you right now it's not quadratic. So the question is find an equation for the function in part A that every time you double it, that every time you tear it, that the output or the number of pieces you have doubles. Go ahead, pause the video, and when you come back, I'll tell you the answer. Okay, hopefully you're back. And again, I'm playing along here, but this video here and the work that we're doing probably should take a lot longer than this video is going to be lasting. But the equation for this one is you started out with, well, you started out with a piece of paper, right? So you started out with, and I'm sorry, my pen's going a little haywire here. Let's see if I can, nope, it's still bleeding on over. I've never had that happen before, but we'll just deal with it. So it happens again, whatever. So here we go. So you started out with one piece of paper and we doubled it. Now every time we need to put X in a spot so we can keep doubling things for each successive tear. And the answer just up front, even if you're guessing from a previous video or something from last week or earlier in the week, that this exponent is up in the exponential spot. Okay, and we have some verbiage here I need to introduce. This is the initial value. That'll always be the initial value, and what you'll find out too, that a lot of times will be the y-intercept commonly. That'll change once we start manipulating the function, but it is the y-intercept. Just 1 second. Guys, sorry, commonly happens when I'm giving these videos. And then this number here is going to be called your growth or decay factor. Now this is just the first couple things. There's actually one more thing I'll introduce, but we're going to call, well, this your growth factor, and this your initial value, and our real formula is going to look like, let me erase this y-intercept thing for a second. You'll figure that out later if you haven't already. But my real function is going to be y equals a b to the x. Now this function will work, and you know the instructions there are saying go ahead and check everything. But watch what happens if you do check everything in green here. For 0 tears, if I plug in 0, notice I'm plugging the input as 0 here into the input, you end up with, well, that's just 1 times, now remember, 2 to the 0, anything to the 0 is just 1. So my answer is 1. And for 1 tear, here's my A. Notice you're always going to have one piece of paper to start with. If 2, now notice I'm doubling there. If I did 1 tear, what happens? 1 times 2, that's just going to equal, I have 2 pieces. And we can keep checking this in green all over the place if you like. After, now notice this is my function here. If I took, 2 tears, then you'd have 1 times 2 times, well, 2 squared is just 4. You have 4 pieces of paper. And what will happen is this is going to be your growth factor. The reason this is happening is every time you're doubling the current amount of piece of papers you have with that tear. So a lot of times they'll say you're doubling, or that's called a doubling factor. And this function is going to be increasing. Okay, something to keep in mind about as we go through these functions. So if they wanted to know, or you were asked, could you do this to determine the 20th tear? You say, oh yeah, no problem. Y equals 1 piece of paper times 2. Remember again, this is my function. And then you just put 20 tears there. I don't know if we could actually get to 20 tears, but on a calculator, and let's go ahead and practice this on a calculator too. If you bumped over, what you'd want to do, now notice what I've been trying to get you to do is to do, we want to do this, 2 times 20, 1 times 2 to the 20th. Sorry, disregard that. So if that's what I wanted you to do, or was asking, usually I'll put this 1 in after the fact. I'll do the 2 to the 20th first. So 2, and then there's a caret feature over here to the 20th power. Now you could hit enter. So you'd have 100, we can write that down somewhere, 1048576. So you'd have 1,048,576 pieces of paper. Now you could take that number, which would be right here, and then multiply that by 1, but you get the same number. Okay, so this would be your answer. So hopefully you're okay with that. And if I asked you to, let's see if I can clear that out here. Let's clear all the drawings, get out of that. And if I did a different share with you and we went back to my problem, let's do this whole thing. We'll go ahead and fill in our answers first. What do we say? 1,048,576 would be the answer for this problem. And then we'd be done. But the big thing, remember, you'll have an initial value. That's usually what you're starting with. A growth or decay factor. And in this case, we are growing or we are increasing. And even if you wanted to go back to your calculator and say, hey, what does this look like? Go ahead and do that too. Y equals, and you could put 1 times 2 to the power of x. Now make sure those of you with calculators are following along. Again, pause the video as needed. But go ahead and zoom so you have a standard viewing window here. So everybody goes by a 10 by 10 window. And you'll see something that's exponential in form that looks just like that. Now be careful. There's some other terminology I need to introduce to you. There is what's called a horizontal asymptote at y equals 0, right here, right along this line here. I'm not showing it very well, but your blue function is y equals 2 to the x. And I'm sorry, again, I'll have to see if I can fix my stylus here, but it got broken over the weekend. But if you had y equals 2 to the x as your function, then this thing's going to shoot up and it's going to be increasing. And more specifically, let's even tell you some more. 1 times 2 to the x was my function, right? Well, if I did 0 tears, we did this already. I'm just trying to get you a well-rounded feeling for what exponential functions are going to look like. 2 to the 0 is just 1. Remember, so my output would be 1. This value here should be the value 0, comma 1. Right? And that's your y-intercept. And I think I might have said that a minute ago, but your initial value out there will look like your y-intercept quite often. Now be careful when you have this function as well. Since I'm just blabbing and trying to spit out everything I can think of, you'll see it written like this quite often. The 1, this part here, won't be written. They'll just expect that you know it's there. But remember, if anything's going to be in this form, y equals a b to the x, that 1 is actually there. They're just assuming that you know a little bit more about it. Okay, so that's an increasing function. Remember, it's headed up. And I guess in the terminology, they'll say exponential functions dominate in the long run, meaning they go up and off to infinity faster than any function on the planet. So if anybody ever tells you that your abilities are increasing exponentially, that should be a pretty big compliment. Okay, so let's go back. Let's do one more, and then we'll conclude this part of the video. Now, if you scroll down, let's do the whole thing again, but let's pretend you were actually sitting in class. And if you're sitting in class, let's say there's 20 people in classes because, I don't know, that's just the size that we're at. So and this we're going to do the same thing. This is going to be tears and pieces of paper. And let's go ahead and change my color back here to blue. Let's say I had 20 pieces of paper. Boy, I changed that back to blue and it stayed green. So I'm going to stay green. So if you had 20 pieces of paper, and again, we're starting all over. We already know our exponential function. We already know we're going to have an exponential function. Remember, a is the initial value, or I call it the IV. And the b is going to be called the growth factor or the decay factor. So I'm already abbreviating. I always think of, remember, y equals mx plus b. I'll erase this in a second. But there's always two things you needed to know, a slope and a y-intercept. Well, you need to know two things here, the initial value and the growth or decay factor. So it's very similar in some aspects in that you need to find out those two constants. But it's also very different in the sense that the constants mean something dramatically different. I can't get that to go away, but let's see if I can use another trick here. So Oop, went back too far. Let's see if we can do that again. Oh, it's not taking it away. I can't figure out what's going on. All right. So as I let you hear my thoughts as I'm going through this and my pen doesn't work, I was trying to erase this. Oh, there it goes. And if we start with 20 pieces of paper in the class, and you still might be able to finish my sentence in this case. So if you don't tear it, you have 20. If everybody tore their piece of paper in half, how many pieces of paper would there be? 40? If we stack them again, go ahead and do some mental math. After two tears, how many pieces of paper would there then be? So hopefully you're telling me 80. Do it again. Everybody in the entire class has 80 pieces of paper, and if everybody tears it in half, they all double the amount of old papers, which should just be 160. And you should be able to fill this chart out without even looking at that point, 320. So again, when you increase the input by 1, the output again doubles. Now, here's the big word. Remember, for a linear function, this function, that slope, had the same constant average rate of change. I hear my daughter. So for linear function, because we need to be able to determine the difference between the two eventually. But for an exponential function, you're going to have a constant percent change. Okay, so that's the big deal. So when you're multiplying to some factor, that thing's there's a multiplier in there, and you can call it your growth factor. That thing's you're gonna be multiplying it by a constant percent change every time. And we could talk about that too at the end of the video here briefly. I just don't want to give you too much. So if you wanted to find an equation for this thing, just like you did the last time, the only difference in this case is that your initial value, I started out with 20 pieces of paper instead of just one. So now I start with 20 pieces of paper. Remember, that's my initial value. And I'm still doubling everything every time. So I have y equals 20 times 2 to the x. And this again is my growth factor. Please, 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 if there's anything you're going to do or rewatch, this might be one of the videos you want to rewatch, especially if you've never seen exponential functions before. Now, for part D, they wanted you to figure out after the 20th tear. You could do that as well and just say 2 to the 20th. And we already knew what that was, really, huh? From before, 2 to the 20th power was, oh gosh, what was it? 1,048,576. So you can do that on your own on a calculator later. But that's how you'd get, just 20 more of those things, or 20 times that number. You'd have 20 million. And we can do it if we really want to do it. 20 million times 1,048,576. So you'd have 209,715,20. So you have 20 million pieces of paper, almost 21 million pieces of paper. And that's typically what we do in class over the course of a period, and then a bunch of exercises, which are coming up on the next video. Now, I will tell you one more thing. Hopefully you got that down. And I just want to expose you to this, and we'll talk about it again. Let me erase this, even though that's the right answer, just because I need some space. Now, something important to know about this growth factor here. Okay, the growth factor, B, is made up of 1 plus the rate of increase or decrease, or I call it the rate. Okay, in this case, my growth factor is 2. And if I wanted to solve for the rate, because that will be the question on your midterms or your finals, or how people talk when they talk about exponential functions, this is that third quantity that makes up the B. The rate is the thing that's going to tell you if your function's increasing or decreasing. Again, you'll hear me say this in the next videos, but if I subtracted 1 from both sides, my rate would be 1, or 1 point, actually, let me write it like this, 1.00, But as far as writing it as a percentage, because we speak about it, if you ever write it, we'll write the rate in decimal form. This is in decimal form. But here, when we talk, it'll be in terms of talk in terms of a percent. Okay, don't worry about this example. We're not doing that. So, really, if I wanted to talk about this last example, and I said, tell me three things about this problem, you would tell me, well, the initial value is 20. That's right here. And it doubles every time that we tear a piece of paper. And then I'm going to ask you, what's the rate of increase or decrease? And you're going to say, hey, because my paper's doubling, you were able to solve for your rate of increase, and it's increasing by 100% each time. So what I like to think of, like if you ever walked into a casino or you've ever seen a movie where people gamble and they say, hey, I went in, I had $100. I came out with 200. I doubled my money. When you double your money, really what's happening is you come out with your first 100 if you were gambling that much money, but you'd come out with another 100% on top of that from what you had when you started. So when you double something, you're really just increasing your original amount by 100%. So let me say that one more time and then we'll end the video. This whole function in this last example, our initial value is 20 because we started with 20 pieces of paper. We then doubled it each time we tore it. So my growth factor was 2. That's how we speak. Now the growth factor is made up of 1 plus the rate. And really, my growth factor is like 1.00. So it's 100% plus my rate of increase or decrease. Now, in this case, my increase or my rate was positive. So it was increasing just because it was positive. This is a big thing here, and I'll even make a different color out of it. It's increasing by 100%. That's the rate of increase. And the things that we'll talk about in the next videos is if it's increasing, your function will look just like what we saw. It'll be increasing. Now, if that number, let's say you went into, um, gosh, and I guess we won't end the video. Give me, I'm still talking. If we went in and, or let's talk about a pair of pants. If you had a pair of pants, for instance, and you had to pay $100 for them, that would be my initial value. But today they took 20% off, just this one time, and it's really a bad example, but I'm trying to use this the term idea of percentages to help you. If I took 20% off, you'd be paying. Would you pay $20 for that pair of pants? For $100 and you took 20% off, you'd really pay 80% of the original price, right? So the reason I put 80 in there is if I wanted my growth factor, and again, this doesn't apply to the pants, it's just trying to get practice with this, figuring out the rate and comparing it to 100. But if you took this 100%, right, this is 1.00, and you subtracted, sorry, I'm messy, my pen again is broken. So if I subtracted, it likes to 1 minus, I took off 20%, 1 minus 0.20, I'd have my new, and this time we'd call it the decay factor. So it's either a growth factor or decay factor, oops, that goes in this spot here, okay? So notice 0.80 is less than 1. So this is decreasing because my B is less than 1. And over here in green, my prior example, it was increasing because my B was greater than 1. So if you're over 100% or 1 point anything, you're going to be increasing, which is going to mean you're going to have a graph like this. Now later on, and I'll stop here, your decreasing function is going to look the same, but it's going to go down. You'll still have an asymptote there, like in the earlier video we said it's at y equals 0, and it will be decreasing because your b is less than 1 or some decimal below 1. And now 0.80, it could be 0.75, or it could look like a fraction, 3/4, but all these numbers would be less than 1, which would force your exponential function to decrease. Okay, So that's a lot of information in one video here. Went a little long, but we'll do some more practice on the next video and some more talking about this. Those three things: your initial value, your growth or decay factor, and your rate of increase or decrease. So until then, keep doing it, or you can go ahead and look forward here, and we're going to practice some more examples. Good job for now.